This chapter deals with oscillations, and we will be looking in particular at simple harmonic motion. Not all motion is simple. The simple comes from the fact that the restoring force, for us, it's going to either be gravity for a pendulum or the spring force for a spring. That force is proportional to the displacement away from equilibrium, and that's what creates this simple harmonic motion. So when you think about simple harmonic motion, I want you to be thinking about a mass attached to a spring, oscillating back and forth, because the mass has been pulled away from equilibrium and released. So at equilibrium, the spring is relaxed. Somebody comes along and pulls it over here to the right, some distance x equals a, where a is called the amplitude, and then they let go. And this mass will then oscillate back and forth between plus a and minus a. And that motion back and forth is simple harmonic motion. The position of the mass at any given time is a sinusoidal function, which comes from solving Newton's second law, but you don't have to solve it. You just have to know this is the answer. And a cosine function, you should probably know what it looks like. Looks just like a sine function, but it starts at x equals a when t equals 0. And it goes between plus a and negative a. And the time it takes to get from plus a right all the way back, so it has to go through 0, over to the left, back through 0, and then over to the right. This time is called the period. And that is the same as the period for circular motion when something is going in a circle. That's the time to go around once. So this is the time for the mass to go back and forth once. Now the omega here in this equation is the same omega as we saw for circular motion. It's the angular frequency, so it's 2 pi f, or 2 pi divided by t. And so that is the quantity that is related to the graph, which is related to the time it takes to go back and forth. Now, as far as the spring goes, omega is determined by how springy the spring is and what the mass attached to the spring is. So this K is the spring constant, which we saw before in chapter 5. And remember, the units for that are newtons per meter. And this is the mass that is attached to the spring. So the bigger the mass, the smaller the frequency. So it's going to go, obviously it's going to, go, it's going to be harder to get that mass going back and forth if it's a big mass. Now this K we also saw from Hooke's law. It comes from the spring force is negative Kx. And the negative is because you pull the mass to the right, if x is positive, the force of the spring is pulling it left. That's why there's a negative. Now this spring force is the only force that acts on the mass, and so this is also equal to m times a. So the acceleration at any given time is equal to negative k over m times x. So there are quite a few questions about this in your book. It seems to like asking about the acceleration as a function of position. Now you can see that if it's going through 0, the position is 0, there is no acceleration. That doesn't mean it's not moving. It's moving the fastest actually there. It's just passing through. There's no force. As soon as it overshoots, now suddenly the force flips over and you have acceleration again. But this is true at any given position in that motion. It also loves to talk about the maximum speed. Now the maximum speed occurs, Vmax occurs when x is 0. It's when it's passing through that 0 point. That's when it's going the fastest. And if you go back to the graph, remember the slope of the graph is equal to the speed. This is the steepest right here when x is 0. So this is the steepest slope. And so that's Vmax. That'd be when it was going to the right. When it's going left, it'd be over here when x is 0. Okay, and when it turns around, the turnaround point here, well, it stops and turns around, V is 0 at the turnaround points. The turnaround. Okay, so those couple of equations you'll need. Also, as far as energy goes, energy is conserved. There's no friction on the surface and you don't lose it in the spring if it's an ideal spring. So it will always say an ideal spring, which means that the total energy is constant. And that total energy is made up of two parts, kinetic plus elastic potential, PE elastic. And so that's equal to a constant. And so 1/2 mv squared plus 1/2 kx squared is equal to a constant. That constant might be any number you want, 100 joules, 50 joules, whatever. Now, how are we going to figure out what that constant is? Well, we can look at different positions. We know that at x equals 0, v equals v max. And so we have that 1/2 mv max squared plus 0 is equal to that constant. So if you know v max, you might be able to get it. We also know at v equals 0, x equals x max. And x max is the amplitude. So we could put that in. 0 plus 1/2 ka squared is equal to the constant. So you could, that's another way to find the constant. So it's either one or the other that you're going to use there to find that constant. Oftentimes they're going to use this. And so they're going to write conservation of energy in general as 1/2 mv squared, any old v, 1/2 kx squared, any old position. And that's going to be the constant 1/2 ka squared. That's a very handy equation, actually, for conservation of energy. And that will come in handy for a lot of the formulae. Now, the V max, from here, you can, if you put those two together, if you put that 1/2 ka squared is the same as 1/2 mv max squared, this is how you get that V max is omega A. And that's super handy. Lots of questions about what is the maximum speed. Okay, so that's the mass on a spring. Similarly, if you have a pendulum, a simple pendulum swinging back and forth like this, that's also simple harmonic motion. That's only if this angle is small, though. Theta has to be small. It doesn't matter what that maximum theta is. Like when I mean small, I mean like up to 10 degrees, that's all. And then this will go back and forth in simple harmonic motion. If you pull it way up and way aside, it's not simple harmonic motion anymore. There's the restoring force is not linear as far as displacement goes because you're dealing with a huge arc. So theta has to be small for simple harmonic motion. If it is small, then the period of the motion is 2 pi root L over G. You may have seen that before. This is the period of a simple pendulum. And it does not matter what the mass is. It's simply that this is the length of the string. And it matters what gravity is. You take a pendulum to the moon, you have a different gravity, you're going to have a different period. And so it doesn't matter how far, as long as you stay within theta being small, if you pull it aside 5 degrees and let it swing or pull it aside 10 degrees, it's going to have the same period. So the period only depends on how long the string is. Okay, that's pretty well all you need for that chapter.